Venus is almost exactly the same size as Earth. It is made of the same rock. It formed in the same cloud of dust, around the same star, roughly the same distance away. For centuries, scientists assumed it was the planet most likely to feel like home. They were catastrophically wrong. Beneath a permanent shell of cloud, Venus hides a surface hot enough to melt lead, crushed under pressure equivalent to being half a mile deep in the ocean, and wrapped in an atmosphere so dense and so chemically hostile that every machine humanity has ever sent there was destroyed within hours. Venus does not just kill, it kills systematically. And the most terrifying part is that scientists now believe it may have once looked almost exactly like the world you're standing on. If this kind of deep science pulls you in, a like and a subscribe genuinely help us keep making these. It costs nothing, and it means more than you think. Also, before we begin, we're now live on Spotify. The link's in the description if you'd like to listen to us wherever you are. Now, are you comfortable? Let's begin. For as long as human beings have watched the sky, one point of light has demanded attention more than any other. It appears at dusk, hanging bright and steady above the horizon, while the last colour drains from the day. It appears again before dawn, holding its position as the sky turns pale around it. It does not flicker like a star. It does not wander unpredictably like a comet. It simply glows, so bright and so unwavering that ancient civilizations on nearly every continent gave it a name reserved for something divine. The Babylonians called it Ishtar. The Greeks eventually connected its evening and morning appearances and identified it as a single object, naming it after Aphrodite. The Romans gave it the name that stuck: Venus, the goddess of beauty, the goddess of love. For thousands of years, that name carried all the hope and romance that human beings projected onto the most beautiful light in their sky. It is the closest planet to Earth. At its nearest, Venus passes within roughly 38 million kilometers of us, closer than Mars ever comes, closer than any other world in the solar system. When the geometry is right, it dominates the twilight sky with a brilliance that outshines everything except the sun and the moon. Even today, people who have never studied a single page of astronomy stop and stare at it without knowing what they are looking at. Venus commands attention. It always has. But for most of recorded history, attention was all anyone could give it, because Venus hides. It is wrapped in a permanent, unbroken shell of cloud so thick and so reflective that no telescope on Earth, no matter how powerful, can see through it to the surface below. That cloud cover is total. There are no gaps, no windows, no momentary clearings where the surface peeks through. From the outside, Venus is a featureless white sphere, brilliant and blank, offering nothing but reflected sunlight and silence. That silence invited speculation, and the speculation, for centuries, leaned overwhelmingly in one direction: hope. The reason for that hope was not sentimental, it was mathematical. Venus is almost the same size as Earth. Its diameter measures approximately 12,104 kilometers, compared to Earth's 12,742. That is a difference of roughly 5%. In planetary terms, 5% is nothing. If you placed a photograph of Venus beside a photograph of Earth, with the cloud layers stripped away and the surfaces unlabeled, the two would look like siblings, not cousins, not distant relatives. Siblings. The mass is similarly close. Venus carries roughly 81.5% of Earth's mass, compressed into a body that is 95% as wide. The density follows accordingly at approximately 5.24 grams per cubic centimeter versus Earth's 5.51. The internal structure, so far as scientists can determine, mirrors Earth's general layout: an iron core, a rocky mantle, a silicate crust. The raw ingredients are the same. The proportions are nearly identical. Even the surface gravity is close. Standing on Venus, you would weigh approximately 91% of what you weigh on Earth. The difference would feel like removing a light backpack, nothing more. Both planets formed from the same disk of gas and dust that swirled around the young sun approximately 4.5 billion years ago. They condensed from the same cloud. They were built from the same materials, in the same region of the solar system, around the same star. Venus orbits at roughly 108 million kilometers from the Sun. Earth orbits at roughly 150 million kilometers. The gap between them is not trivial, but it is modest by the standards of planetary spacing. In the grand architecture of the solar system, Venus and Earth are neighbors sharing a fence. This is why scientists called Venus the twin of Earth. Not as poetry, as description. On paper, before anyone knew what lay beneath those clouds, Venus was the single most Earth-like object in the known universe. Same size, same weight, same rock, same star. Closer to that star, certainly, which meant warmer. But in the minds of many astronomers, warmer simply meant tropical. And tropical, in the age before spacecraft, meant possibility. The romance with Venus began early, and it ran deep through the history of astronomy. In 1610, Galileo Galilei turned his telescope toward Venus and observed something that would help overturn the prevailing model of the universe. He watched the planet go through phases, the same cycle of crescent, half, gibbous, and full that the moon displays from Earth. Under the old Ptolemaic system, which placed Earth at the center of all celestial motion, Venus could not have displayed a full set of phases. The fact that it did was consistent only with a solar-centered model in which Venus orbited the Sun, sometimes passing between us and the star, sometimes swinging around to the far side. It was among the strongest pieces of observational evidence supporting the Copernican revolution. Venus did not just captivate observers with its beauty, it helped rewrite the rules of the cosmos. But even Galileo could not see past the clouds. The surface remained hidden. And as telescopes improved over the next 3 centuries, that fact did not change. Astronomers could measure the planet's size. They could track its orbit with extraordinary precision. They could confirm that it had an atmosphere, because they could watch starlight dim and redden as it passed through the Venusian limb during transit events. In 1761, the Russian polymath Mikhail Lomonosov observed just such a transit and became the first person to formally describe Venus's atmosphere, noting the halo of refracted light that appeared around the planet's disk as it crossed the face of the Sun. An atmosphere meant weather. Weather meant water. Water meant possibility. The logic was relentless, and for nearly 200 years, nobody could disprove it. The cloud cover that blocked the view became, paradoxically, a canvas for optimism. If you cannot see the surface, you can imagine whatever you like. And for more than a century, what scientists and the public imagined was a world of water. The reasoning went like this. Venus is closer to the Sun, so it receives more energy. More energy means more evaporation. More evaporation means more clouds. The clouds we see are thick and white, similar to water vapor clouds on Earth. Therefore, beneath those clouds, Venus must be a warm, wet world. probably covered in swamps, rainforests, or shallow seas. The logic felt airtight. It was entirely wrong, but it felt airtight. In the late 1800s and early 1900s, this vision of a lush, humid Venus saturated both popular culture and serious scientific literature. Percival Lowell, the same astronomer famous for his claims about canals on Mars, wrote about Venus as a world where conditions might support life. The Swedish chemist Svante Arrhenius had gone further decades earlier, proposing that Venus might resemble a younger version of Earth, covered in swamps similar to those of the Carboniferous period, with conditions ripe for life to thrive. He imagined dense vegetation, moisture dripping from every surface, and a world where the energy of a closer sun had simply accelerated the biological clock, producing a planet more alive than our own rather than less. Science fiction authors embraced this vision without reservation. Edgar Rice Burroughs, the creator of Tarzan, set an entire series of novels on a Venus teeming with oceans and alien civilizations. C.S. Lewis imagined a Venusian world of floating islands on a warm global sea. Ray Bradbury wrote Venus as a rain-soaked planet of relentless downpour. In film, in pulp magazines, in radio dramas, and in the imaginations of millions, Venus was the wet planet, the green planet, the world most likely to harbor life in our solar system. Even well into the 1950s, reputable astronomy textbooks describe Venus as a plausible candidate for a habitable world, possibly hosting primitive vegetation or microbial life in its presumably warm and wet environment. This was not fringe thinking. This was mainstream. Venus was the safe bet. Mars was dry and cold, with a thin atmosphere and visible deserts. The outer planets were gas giants with no solid surface. Mercury was a scorched rock, too close to the sun. Venus, by elimination and by measurement, was the one place in the solar system that seemed most likely to welcome a visitor. The cloud cover that prevented direct observation became a kind of promise. Whatever was underneath, it had to be interesting. It had to be alive. The first hint that something was wrong came not from a spacecraft, but from a radio telescope. In the late 1950s, astronomers at the Naval Research Laboratory in Washington pointed radio receivers at Venus and detected microwave emissions coming from the planet. The work was led primarily by Cornell Mayer and his colleagues, who published their findings in 1958. Microwave radiation at those wavelengths is associated with thermal emission, which means the intensity of the signal is directly related to the temperature of the source. When the researchers calculated the temperature that would be required to produce the signal they were receiving, the number made no sense. The microwave data pointed to a surface temperature of roughly 600 degrees Kelvin. That is over 300 degrees Celsius. Hotter than an industrial oven. Hotter than the melting point of LED. Hotter than anything that could plausibly exist on a world with oceans and rainforests. The scientific community was skeptical. The measurement could have been wrong. The signal could have originated from the upper atmosphere rather than the surface. There were models that attempted to explain the readings without invoking extreme surface heat, proposing instead that Venus might have a dense ionosphere that was producing the emission. A young Carl Sagan, then a graduate student at the University of Chicago, argued the opposite case. He published work in the early 1960s suggesting that a massive greenhouse effect could explain the radio observations, that the extreme temperatures were real and were produced by an atmosphere dominated by carbon dioxide and water vapor trapping solar energy with devastating efficiency. but his was a minority voice at the time. The ocean hypothesis was not abandoned, it was defended. Scientists had invested decades of assumptions into the idea of a wet, temperate Venus, and one strange radio reading and one graduate student's greenhouse calculation were not enough to overturn it. The debate split the community. Some clung to the possibility that the microwave readings were atmospheric artifacts. Others began, reluctantly, to consider the possibility that the planet they had romanticized for a century was something else entirely. Then, Mariner 2 arrived. On the 14th of December, 1962, the American spacecraft Mariner 2 completed a flyby of Venus. It was the first successful interplanetary mission in history. The spacecraft carried, among other instruments, a microwave radiometer and an infrared radiometer designed to measure the thermal properties of Venus from close range. What it found was devastating. The microwave data confirmed what the ground-based radio telescopes had suggested. The surface of Venus was extraordinarily hot. The readings were consistent with a temperature of approximately 460 degrees Celsius across the entire planet. Not in one region. Not on the day side only. Everywhere. The infrared radiometer confirmed that the cloud tops were cold, roughly minus 35 to minus 45 degrees Celsius. But the microwave signal from below those clouds told a completely different story. Beneath the beautiful white veil, Venus was burning. The implications landed like a verdict. Sagan had been right. The greenhouse model fit. The ionosphere model did not. The data was clear and it was consistent. And within a few years, the scientific consensus shifted decisively. Venus was not a tropical paradise. It was not a swamp world. It was not a sister planet waiting for visitors. It was something no one had imagined. A world almost identical to Earth in every structural sense, wrapped in an atmosphere so thick and so efficient at trapping heat that its surface had been baked beyond the melting point of common metals. Centuries of optimism collapsed in a single flyby. The Venus that humanity had dreamed about for generations did not exist, and had probably never existed. What was actually there was worse than anyone had feared. The cultural shock was considerable. Science fiction writers had to abandon their Venusian jungles overnight. Textbooks were revised. The word twin, which had carried connotations of warmth and kinship, acquired a darker edge. Venus was still Earth's twin, but now the resemblance was disturbing kind. The kind where you look at something that should be familiar and realize it has gone horribly wrong. Astronomers who had spent careers studying Venus under the assumption that it was a candidate for life had to reconfigure their entire research programs. The Mariner 2 results didn't merely update a number in a database. They destroyed a worldview that had persisted for centuries and replaced it with something far more unsettling. The knowledge that the most Earth-like planet in the solar system was also the most lethal, and that the difference between the two outcomes, between Earth and Venus, was not written in their rocks or their orbits, but in an invisible layer of gas that nobody had been able to see through until it was measured from the inside. Subsequent missions confirmed and refined the picture. The Soviet Venera probes, launched throughout the 1960s and 70s, descended into the atmosphere and sent back increasingly detailed profiles of the temperature, pressure, and chemical composition at every altitude. The American Pioneer Venus mission in 1978 added an entirely new dimension to the data. It consisted of two spacecraft, an orbiter that studied the planet from above, and a multi-probe carrier that released 4 separate descent vehicles, into the atmosphere simultaneously. The 4 probes entered at widely separated locations across the planet. One near the North Pole, one on the day side, one on the night side, and one near the equator. All 4 transmitted atmospheric profiles as they fell, and all 4 recorded the same punishing conditions at every location. The extreme temperatures and pressures were not regional anomalies, they were global. The orbiter, meanwhile, delivered measurements of the cloud chemistry, the atmospheric circulation, and the thermal radiation escaping from the top of the atmosphere. It confirmed that the sulfuric acid clouds were planet-wide and permanent, and that the amount of infrared energy escaping to space was far less than the amount entering the system, direct orbital confirmation of the greenhouse mechanism that was trapping heat below. Every dataset told the same story. The surface was crushingly hot. The atmosphere was overwhelmingly carbon dioxide. And the pressure at the ground was a number that, when first transmitted back to Earth, was rechecked multiple times because nobody believed it. The number bears repeating because of what it implies. 465 degrees Celsius is the accepted modern measurement of Venus's mean surface temperature, confirmed and refined by subsequent missions. At that temperature, lead melts, zinc melts, tin melts. Certain aluminum alloys begin to soften. The surface of Venus is not merely hot in the way that a desert is hot, or a volcanic vent is hot. It is hot in the way that the inside of a kiln is hot, uniformly, constantly, and across the entire planet, with no relief at the poles, no cooling at night, no seasonal variation, and no escape. And here is the detail that transforms the measurement from surprising to disturbing. Mercury, the planet closest to the Sun, orbits at an average distance of roughly 58 million kilometers from the solar surface. Venus orbits at roughly 108 million kilometers. That means Venus is nearly twice as far from the Sun as Mercury is. By every intuitive standard, Mercury should be the hotter planet. It receives vastly more solar radiation per unit of surface area. On its sunlit side, Mercury's surface can reach approximately 430 degrees Celsius, which is blisteringly hot by any earthly standard. But on its night side, temperatures plummet to approximately negative 180 degrees Celsius, because Mercury has almost no atmosphere to retain heat. Energy arrives from the sun, and when the surface rotates away, that energy radiates back into space almost immediately. Mercury is hot when the sun is shining on it, and bitterly cold when it is not. The temperature swings are extreme and immediate, like a bare rock in a fire that cools the moment you pull it away from the flame. Venus does not work this way. Venus is 465 degrees Celsius on the day side. It is 465 degrees on the night side. It is 465 degrees at the equator, 465 degrees at the poles, 465 degrees at midnight, and 465 degrees at noon. The temperature does not meaningfully vary across the entire surface of the planet. Venus is locked in a thermal state so uniform and so extreme that it outperforms the innermost planet in the solar system by a significant margin, despite receiving less than half the solar energy. That fact alone should stop anyone who hears it for the first time. A planet nearly twice as far from the Sun as Mercury is hotter, everywhere, at all times, than the hottest point on Mercury ever gets. Distance from the star is not the determining factor. Something else is. The Soviet Union was the first to find out what that something else felt like from the inside. Beginning in the early 1960s, the Soviet space program launched a series of missions to Venus under the name Venera. The early attempts were disasters. Venera 1 lost contact during its cruise phase. Subsequent missions failed during atmospheric entry, crushed or overheated long before they reached the surface. The engineers had designed their spacecraft to survive conditions that were harsh but manageable, consistent with the old models of a warm, cloudy world with moderate pressure. Venus destroyed those spacecraft the way a deep ocean trench would destroy a submarine built for shallow water. The conditions were not slightly beyond expectations. They were categorically beyond anything the engineers had prepared for. As mission after mission failed, the Soviet engineers adapted. They overbuilt. They reinforced pressure vessels. They added cooling systems. They designed landers that could survive not just heat, but heat combined with immense atmospheric pressure, combined with chemical exposure. Each failed mission returned data during its descent, and each set of descent data told the same story. The atmosphere was getting denser, hotter, and more hostile with every kilometer closer to the surface. The descent profiles that the early probes transmitted before dying became the blueprints for their successors. Venera 4 in 1967 transmitted atmospheric data during its descent but was crushed at an altitude of roughly 25 kilometers, never reaching the surface. Its instruments recorded a temperature of over 260 degrees Celsius and a pressure of roughly 22 Earth atmospheres at the point where the signal died, and the surface was still far below. Venera 5 and Venera 6, launched in 1969, met similar fates. Each one descended deeper than the last, each one recording higher temperatures and greater pressures, and each one was destroyed before it reached the ground. The engineers were building a portrait of the atmosphere one dead spacecraft at a time. Then, in December of 1970, Venera 7 became the first spacecraft to transmit data from the surface of another planet. The story of how it survived that landing, and the near miracle by which its signal was recovered from what appeared to be noise, belongs later in this account. What matters for now is what the data said. Surface temperature, roughly 475 degrees Celsius. Surface pressure, approximately 90 Earth atmospheres. 90 times the weight of air that presses down on you at sea level. The numbers were not ambiguous. They were not open to interpretation. They were a death certificate for every model of Venus that had ever included the word habitable. What followed over the next 15 years was a campaign of confirmation so thorough that no room for hope remained. Venera 8 landed in 1972 and measured surface light levels, proving the clouds were not completely opaque. Venera 9 reached the surface in 1975 and returned the first photograph ever taken on another planet. Venera 13 in 1982 survived longer than any lander before or since and transmitted the first color images. In total, 10 Soviet spacecraft touched the surface of Venus between 1970 and 1985. Every single one was eventually destroyed by the conditions surrounding it. The longest any of them lasted was just over 2 hours. No mission returned encouraging news. No lander found a cooler region, a sheltered basin, a chemical anomaly that might soften the verdict. Every site told the same story. The surface was volcanic basalt, barren and still, baked under a sky that glowed with trapped heat and pressed under an atmosphere so dense it blurred the line between gas and fluid. The conditions were not merely harsh. They were uniform in their harshness, the same punishing environment at every latitude, every longitude, every hour of the Venusian day. The implications extended far beyond Venus itself. Before these missions, the prevailing assumption in planetary science had been that any rocky world of the right size, orbiting at a reasonable distance from a stable star, had a plausible chance of developing conditions favorable to life. Venus shattered that assumption. Here was a planet that met every structural criterion for habitability: the size, the mass, the rock, the star, and had arrived at a surface state so extreme that the word inhospitable was laughably inadequate. The question shifted. It was no longer about whether Venus could support life. It was about how a world with every apparent advantage had produced the most lethal surface in the inner solar system. And more disturbingly, it raised the possibility that Earth's own habitability was not a given, not a default outcome of being the right size in the right place, but something that had to be actively maintained by processes that could, under different circumstances, fail. That realization that a planet's habitability is not written in its size, but in the behavior of its atmosphere, is what transforms Venus from an interesting neighbor into something more unsettling. No nation has successfully operated on that surface in over 40 years. The engineering that will be required to survive there has not yet been built, and the reasons why are written in the air above the ground, not in the ground itself. Take a moment and hold all of that together. Venus is 95% the diameter of Earth. It is 81.5% of Earth's mass. It is made of the same rock, born from the same cloud of primordial dust, orbiting the same star. On every physical measurement that defines what a planet is, Venus is Earth's closest match. There is no other body in the known universe that comes as close. And this closest match, this twin, this sibling, maintains a surface temperature that exceeds 460 degrees Celsius, a pressure that would crush a nuclear submarine, an atmosphere so dense that its lower layers behave less like gas and more like a slow, corrosive fluid, and a chemical environment so hostile that hardened titanium landers engineered by one of the most determined space programs in history could not last a full afternoon. That is the contradiction at the center of this story, and it is not a small one. The most Earth-like planet in the solar system is also the most lethal. Not the most distant, not the coldest, not the most exotic. The one that looks the most like home is the one that would kill you fastest. The question is how? How does a planet that shares nearly every physical trait with Earth end up with a surface that functions like a furnace sealed inside a pressure chamber? The answer is not at the surface. The surface is a consequence. The cause is above it, wrapped around the planet in a blanket so thick and so thermally efficient that once it formed, the outcome was irreversible. Venus does not have weather. It has a verdict. And that verdict was delivered by an atmosphere that most people have never had properly explained to them. Because what happened in that atmosphere is one of the most complete and most terrifying planetary catastrophes ever documented in this solar system. What follows will take you inside it. To understand what happened to Venus, you have to stop thinking about temperature as the problem. Temperature is the symptom. The problem is the air. Not air in the way you experience it. Not the thin, transparent, nearly weightless mixture of nitrogen and oxygen that fills your lungs right now without you noticing. The atmosphere of Venus is a different category of substance entirely. It is a blanket so massive, so dense, and so thermally efficient that it has converted an entire planet into a heat engine with no exhaust valve. Everything that follows in this story, every destroyed lander, every measurement that defies expectation, Every lethal feature of the Venusian surface traces back to what is hanging above it. The atmosphere is not a detail of Venus. It is the explanation. Start with composition. The atmosphere of Venus is approximately 96.5% carbon dioxide. The remaining 3.5% is almost entirely nitrogen. Everything else, sulfur dioxide, argon, water vapor, carbon monoxide, traces of helium and neon, amounts to fractions of a single percent. In practical terms, the Venusian atmosphere is a nearly pure column of carbon dioxide stretching from the surface to an altitude of roughly 250 kilometers. Now, consider the mass. The total mass of the Venusian atmosphere is approximately 4.8 times 10 to the 20th kilograms. That number means nothing to most people, so here is a comparison that might. The total mass of all the water in all of Earth's oceans, every ocean, every sea, every drop, is roughly 1.4 times 10 to the 21st kilograms. The atmosphere of Venus weighs approximately 1/3 as much as every ocean on Earth combined. Imagine compressing the volume of 1/3 of Earth's oceans into gas and draping it over a planet. That is the mass hanging above the surface of Venus. That is the weight pressing down on every square centimeter of rock below. And it is almost entirely carbon dioxide. On Earth, carbon dioxide makes up approximately 0.04% of the atmosphere. Less than half of 1/10 of 1%. That tiny fraction is enough to warm the planet by roughly 33 degrees Celsius, above what its temperature would be if the atmosphere were transparent to infrared radiation. 33 degrees is the difference between a frozen, ice-covered world and the habitable planet you live on. That is the greenhouse effect in its benign form. A thin veil of heat-trapping gases keeping temperatures within the range, where water stays liquid and chemistry stays productive. On Venus, the greenhouse effect is not benign, it is totalizing. Here is how the mechanism works, stripped to its essentials. The sun emits energy across a wide spectrum, but the bulk of what reaches a planet's surface arrives as visible light. Visible light passes through carbon dioxide with relative ease. The molecules do not absorb it efficiently. So sunlight enters the Venusian atmosphere, penetrates the cloud layers, and reaches the ground. The surface absorbs that energy and warms. As it warms, it re-emits energy, but not as visible light. Warm surfaces radiate energy in the infrared part of the spectrum, at longer wavelengths than visible light. And carbon dioxide is extremely effective at absorbing infrared radiation. The molecules capture the outgoing energy, vibrate, and re-emit it in all directions, including back downward toward the surface. The surface absorbs that returned energy, warms further, emits more infrared, which is captured again, returned again, absorbed again. On Earth, this cycle reaches an equilibrium. The thin layer of carbon dioxide and other greenhouse gases traps some heat, but enough infrared energy escapes through the top of the atmosphere to balance what comes in from the sun. The planet settles at a stable temperature. On Venus, the cycle never reached equilibrium. It ran away. The term scientists use for this is the runaway greenhouse effect, and the name is precise. A runaway process is one where the output feeds back into the input and accelerates the system beyond any natural stopping point. On Venus, more carbon dioxide meant more trapped heat. More trapped heat meant higher surface temperatures. Higher surface temperatures meant that any surface water would evaporate, adding water vapor to the atmosphere. Water vapor is also a potent greenhouse gas. More water vapor meant more heat trapped, which meant more evaporation, which meant more water vapor, which meant more heat. The cycle fed itself. At some point in Venus's early history, this loop crossed a threshold. The exact timing is debated. Some models place it within the first few 100 million years of the planet's formation. Others suggest Venus may have maintained moderate conditions for longer before the tipping point arrived. But whenever it happened, the consequences were the same. The water evaporated. All of it. Every ocean, every lake, every drop. The moisture that had been on the surface moved into the atmosphere, and once it was there, the upper atmosphere finished the job. High-altitude ultraviolet radiation from the sun broke the water molecules apart in a process called photodissociation. Each molecule of water consists of 2 hydrogen atoms and 1 oxygen atom. When ultraviolet light strikes a water molecule in the upper atmosphere with enough energy, it splits the molecule, liberating the hydrogen. Hydrogen, the lightest element in the universe, rises to the top of the atmosphere where it reaches escape velocity and drifts into space. This is not a recoverable process. Once a hydrogen atom leaves the planet's gravitational influence, it is gone permanently. It will not return. It will not be replaced. Every hydrogen atom that escapes is a piece of a water molecule that can never be reassembled. Oxygen left behind, combined with other elements, or was gradually lost through additional processes over geological time. But the critical loss was the hydrogen. Without hydrogen, there is no water. And without a mechanism to replenish it, every molecule of water that the sun's radiation destroys is subtracted from the planet's total inventory forever. The process is relentless, continuous, and one-directional. It operates as long as the sun shines, as long as water vapor exists in the upper atmosphere, and as long as there is no magnetic field strong enough to deflect the solar wind that assists in stripping the lightest gases away. Venus has no such magnetic field. The stripping continued unimpeded for billions of years. This is confirmed by measurement. The ratio of deuterium to regular hydrogen in the Venusian atmosphere is roughly 100 to 150 times higher than the ratio found on Earth. Deuterium is a heavier form of hydrogen, containing 1 proton and 1 neutron instead of just 1 proton. When water molecules are broken apart by ultraviolet light, regular hydrogen escapes more easily than deuterium because it is lighter. Over billions of years of water loss, the lighter hydrogen preferentially escapes, leaving the heavier deuterium behind in disproportionate concentrations. The deuterium enrichment on Venus is a chemical fingerprint of massive ancient water loss. It does not prove that Venus once had oceans in the way Earth does now, but it demonstrates beyond serious doubt that Venus once had vastly more water than it currently possesses, and that the water was destroyed. The enrichment ratio tells scientists roughly how much hydrogen has been lost. The answer is enormous. Venus has been bleeding water into space for the majority of its existence. And today, the traces of water vapor remaining in the atmosphere amount to roughly 20 parts per million. Effectively 0. The loss of water was not merely a surface event, it was an atmospheric catastrophe, because water is the key ingredient in the only planetary process that can remove carbon dioxide from an atmosphere on geological timescales. On Earth, this process is called the carbonate-silicate cycle, and it works like a thermostat. Carbon dioxide dissolves in rainwater, forming a weak acid called carbonic acid. That acidic rain falls on silicate rocks and chemically weathers them, pulling carbon out of the atmosphere and locking it into carbonate minerals that wash into the oceans and eventually settle on the seafloor. Over millions of years, plate tectonics subduct those carbonate-rich sediments into the mantle, where heat and pressure release the carbon dioxide back into the atmosphere through volcanic eruptions. The cycle is slow, but it is self-correcting. If carbon dioxide levels rise, temperatures increase, which increases rainfall, which increases weathering, which pulls more carbon out of the atmosphere, which lowers temperatures. If levels drop, temperatures fall, rainfall decreases, weathering slows, and volcanic carbon dioxide accumulates until the balance is restored. Earth has been running this thermostat for billions of years. It is not perfect. There have been ice ages and hot periods, but the system has kept the planet within a range where liquid water can persist on the surface, and that persistence is what keeps the thermostat running. Water is both the mechanism and the condition. Without liquid water, there is no rain. Without rain, there is no chemical weathering. Without weathering, there is no way to pull carbon dioxide from the atmosphere. The cycle breaks. On Venus, the cycle broke. When the water was lost, the thermostat shut off. Carbon dioxide that was released by volcanic activity, and Venus has been volcanically active throughout its history, had nowhere to go. It could not be absorbed by rain that no longer existed. It could not be locked into carbonate minerals on a surface with no liquid water to drive the chemistry. It accumulated. Layer by layer, eruption by eruption, over hundreds of millions of years, the atmosphere thickened. And as it thickened, it trapped more heat, which ensured that any remaining water would be vaporized, which ensured that the weathering cycle could never restart, which ensured that the carbon dioxide would continue to accumulate. The feedback loop was closed permanently. Here is a fact that drives this home. Earth and Venus have roughly the same total inventory of carbon. On Earth, the vast majority of that carbon is locked in carbonate rocks, limestone, chalk, marble, and other minerals buried in the crust and cycled through the mantle by plate tectonics. Only a tiny fraction resides in the atmosphere. If you could liberate all of the carbon currently stored in Earth's rocks and release it as carbon dioxide into the atmosphere, the resulting atmospheric pressure would be remarkably close to that of Venus. The carbon is the same, the quantity is the same. The difference is where it sits. On Earth, it is in the ground. On Venus, it is in the air. Let that settle for a moment. Earth is not chemically safer than Venus. It does not have less carbon. It does not possess some special elemental advantage. Earth has exactly the same raw material for a Venusian atmosphere already present inside its crust. The only thing keeping that carbon underground is the mechanical process of weathering and subduction, the thermostat. Remove the water, stop the cycle, and the carbon has nowhere to go but up. It rises over millions of years, molecule by molecule, eruption by eruption, until the atmosphere looks indistinguishable from the one currently smothering Venus. Earth is not immune to this outcome. It is actively, continuously preventing it every day through processes most people have never heard of. The thermostat kept Earth's carbon buried. Venus lost its thermostat, and the carbon rose. The result is the atmosphere that exists today, 92 to 93 times the pressure of Earth's atmosphere at sea level. A column of gas so dense that standing on the surface of Venus would feel equivalent to standing beneath roughly 900 meters of ocean water on Earth. The density of the atmosphere near the surface is approximately 65 kilograms per cubic meter. For comparison, the density of Earth's atmosphere at sea level is roughly 1.2 kilograms per cubic meter. The air on Venus is more than 50 times denser than the air you are breathing right now. At that density, the distinction between gas and fluid begins to blur. The lowest layers of the Venusian atmosphere do not behave the way gas behaves in any environment you have experienced. They push, they resist, they transmit pressure the way a liquid transmits pressure. Moving through the near-surface atmosphere of Venus would not feel like walking through air. It would feel like wading through a medium that has weight and resistance, something closer to a slow, hot, invisible current pressing against you from every direction. And the thermal consequences of that density are staggering. A dense atmosphere does not merely trap more infrared radiation per molecule, it fundamentally changes how heat distributes across a planet. On Earth, the atmosphere is thin enough that significant temperature differences exist between the equator and the poles, between day and night, between summer and winter. Energy arrives from the sun unevenly, and the atmosphere redistributes it, but imperfectly. Temperature gradients persist. They drive weather. They create seasons. They make certain places warm and other places cold. On Venus, the atmosphere is so massive and so thermally conductive that it erases gradients almost entirely. This is why the surface temperature barely varies across the entire planet. The atmosphere acts as a thermal buffer of extraordinary capacity. It absorbs energy from the sunlit side and circulates it to the dark side with such efficiency that the night side temperature is functionally identical to the day side temperature. There is no cool hemisphere. There is no winter. There is no relief. The mechanism behind that circulation is itself one of the most baffling phenomena in planetary science. It is called atmospheric superrotation, and it should not exist according to simple models, yet it does. Venus rotates almost inconceivably slowly. A single rotation of Venus on its axis takes approximately 243 Earth days. That is longer than the planet's orbital period around the Sun, which is roughly 225 Earth days. Venus's day is longer than its year, and the rotation is retrograde, meaning it spins in the opposite direction from nearly every other planet in the solar system. On Venus, the sun rises in the west and sets in the east, if you could see the sun at all through the opaque cloud deck. At the surface, the winds are feeble, barely a meter per second, a slow drift, but travel upward through the atmosphere, and the picture changes dramatically. At cloud level, roughly 50 to 70 kilometers above the ground, the atmosphere is moving at speeds of up to 360 kilometers per hour. The entire upper atmosphere circles the planet in approximately 4 Earth days. 4 days. The planet itself takes 243 days to complete a single rotation, but its upper atmosphere whips around 60 times faster. This is the superrotation, and it is one of the most extreme examples of atmospheric decoupling from surface rotation known in planetary science. The atmosphere is essentially detached from the ground below, operating on its own thermal and dynamic logic, driven by the absorption of solar energy in the cloud layers and by poorly understood wave dynamics that transfer angular momentum upward through the atmospheric column. The superrotation has been confirmed repeatedly by observation. The Japanese Akatsuki orbiter, which arrived at Venus in 2015 after a dramatic orbital insertion recovery, spent years tracking cloud patterns in the upper atmosphere and measuring wind speeds at various altitudes. Its data confirmed the 4-day circulation period and revealed additional complexity. Massive planetary-scale wave structures, standing bow-shaped features in the upper atmosphere caused by mountain ranges on the surface far below, and transient vortex formations near the poles that resemble hurricanes, but operate under entirely different physics. The atmosphere of Venus is not merely thick, it is dynamic, structured, and energetically decoupled from the slowly turning world beneath it in ways that planetary scientists are still working to explain. The superrotation matters for the temperature story because it is one of the mechanisms that carries heat from the day side to the night side so efficiently. Even though Venus's solar day is 117 Earth days long, meaning one hemisphere faces the sun for nearly 2 months at a stretch, the upper atmosphere redistributes the absorbed energy around the planet in 4 days. By the time that energy works its way down through the dense lower layers, the temperature difference between day and night has been smoothed to near zero. The superrotation acts as a conveyor belt for thermal energy, ensuring that no part of the planet ever cools down. The combination of slow rotation and orbital period produces a solar day, the time from one sunrise to the next, of approximately 117 Earth days. That means the sunlit side of Venus faces the sun continuously for roughly 58.5 Earth days, before rotating into darkness for another 58.5 days. On any planet with a thin atmosphere, this would create extreme temperature contrast between the day and night hemispheres. Mercury, with its slow rotation and negligible atmosphere, shows exactly this pattern, veering between blistering heat and deep cold with every rotation, because it has no atmospheric mass to buffer the difference. Venus does not swing. Venus does not vary. Because the atmosphere is so massive, and because the superrotation circulates energy so thoroughly, the 58-day exposure to sunlight and the 58-day absence of it produce no detectable difference at the surface. The atmosphere overwhelms the rotation. It overwhelms the geometry. It overwhelms everything. Whatever energy enters the system stays in the system, circulated and recirculated through a dense carbon dioxide blanket that refuses to let it leave. And above the dense lower atmosphere sit the clouds. The clouds of Venus are not water clouds. They are composed primarily of sulfuric acid droplets, concentrated at altitudes between roughly 48 and 70 kilometers above the surface. The cloud deck is thick, layered, and permanent. It is not a single uniform sheet. It is a structured system with at least 3 distinct layers, each with different particle sizes, densities, and chemical properties. The upper cloud layer, between roughly 60 and 70 kilometers, contains fine sulfuric acid droplets approximately 1 micrometer across. The middle layer, from roughly 50 to 60 kilometers, is denser, with larger droplets. The lower layer, from 48 to 50 kilometers, is the thickest and most opaque, containing the highest concentration of acid by volume. Below 48 kilometers, a thin haze extends further down before giving way to the clear, superheated lower atmosphere. The cloud system as a whole is approximately 20 kilometers deep, far thicker than any persistent cloud formation on Earth, and it wraps the entire planet without a single break. There are no clear patches. There are no gaps between the poles and the equator. The blanket is total. It reflects approximately 75% of all incoming sunlight back into space before it ever reaches the surface. This is why Venus appears so bright from Earth. It is one of the most reflective objects in the solar system. Its albedo, the fraction of incoming light it reflects, is roughly 0.77. By comparison, Earth's albedo is approximately 0.3. This creates a paradox that is important to understand. Venus reflects far more sunlight than Earth does. Only about 25% of the solar energy that reaches Venus actually penetrates the clouds and makes it to the surface. If you calculate the temperature of Venus based solely on the energy that reaches the ground, you would get a number far lower than what is actually measured. The predicted temperature, accounting for distance from the sun and reflectivity, would be something in the range of -40 to -10 degrees Celsius. Cold, potentially habitable, possibly even frozen. The actual surface temperature is 465 degrees Celsius. The difference between the predicted temperature and the actual temperature, a difference of roughly 500 degrees, is the greenhouse effect. That 500-degree surplus is entirely the work of the atmosphere. The clouds that reflect most of the sunlight away simultaneously seal the planet so effectively that the small fraction of energy that does get through becomes trapped in a thermal prison with no exit. Venus receives less energy at its surface than Earth does, and yet it is hotter than any other rocky surface in the solar system. The atmosphere is that powerful. There is an additional mechanism operating within the atmosphere that adds to the thermal extremity, and it is purely physical. It is called adiabatic heating, and it operates independent of the greenhouse effect. When gas is compressed, it heats up. This is not a chemical reaction. It is a direct consequence of the physics of pressure. You have likely felt this yourself. If you have ever pumped a bicycle tire with a hand pump and noticed the barrel of the pump growing warm under your fingers, you have experienced adiabatic heating. The air inside the pump is being compressed, and the compression converts mechanical energy into thermal energy. The molecules are forced closer together, they collide more frequently and more energetically, and the temperature rises. No flame is involved, no chemical change, just pressure-producing heat. That same principle operates in any atmosphere. As you descend deeper, the weight of the gas above increases, compressing the gas below and raising its temperature. On Earth, this effect is modest. The atmosphere is thin, and the pressure increase from the top of a mountain to sea level is small. The temperature increase from adiabatic compression in Earth's lower atmosphere is real but not dramatic. You do not feel the air get noticeably warmer as you walk downhill. On Venus, the atmosphere is so deep and so dense that the adiabatic heating effect is enormous. The temperature increases by roughly 8 degrees Celsius for every kilometer of descent through the lower atmosphere. Starting from the relatively cool cloud tops at around -40 degrees Celsius, the temperature rises steadily and relentlessly as you descend through 60, 70, 80 kilometers of increasingly dense gas. By the time you reach the surface, the accumulated adiabatic heating has added hundreds of degrees to the temperature. This is not heat from the sun. This is heat generated by the sheer weight of the atmosphere pressing down on itself. The greenhouse effect and adiabatic heating work together. The greenhouse effect keeps the total energy budget of the atmosphere high by preventing infrared radiation from escaping. The massive depth and density of the atmosphere then distribute that energy vertically through compression, ensuring that the surface, sitting at the bottom of 92 atmospheres of carbon dioxide, experiences the full thermal consequence of both mechanisms simultaneously. Neither one alone would produce a surface temperature of 465 degrees. Together they produce a planet where the surface has been baking at a nearly constant temperature for what may be hundreds of millions of years. And that constancy is perhaps the most frightening feature of all. The system is stable. Not stable in the sense that it is healthy, but stable in the sense that it is self-maintaining. The runaway greenhouse effect did not produce a temporary hot period that will eventually correct itself. It produced a new equilibrium, a permanent state of extreme heat, maintained by the same feedbacks that created it. The carbon dioxide is not going anywhere. There is no process operating on Venus that can remove it. The water that could have driven a weathering cycle is gone. The plate tectonics that could have buried carbon in subducted rock either never developed on Venus in the way they did on Earth, or they shut down at some point in Venus's geological history. The surface of Venus shows evidence of catastrophic resurfacing events, periods where massive volcanic activity appears to have repaved large portions of the planet within relatively short geological windows, but no evidence of the slow, continuous recycling of crust that characterizes Earth's tectonic system. Without water, without tectonics, without any mechanism to draw carbon dioxide out of the atmosphere, the thermal state of Venus is locked. The atmosphere is not a temporary aberration. It is a permanent condition. The planet crossed a line from which there is no return using any process that planetary science currently recognizes. Consider what this means in full. Venus has an atmosphere that is 96.5% carbon dioxide, 92 to 93 times the pressure of Earth's, dense enough to behave like a fluid near the surface, thermally efficient enough to erase all temperature variation between day and night and between equator and poles, deep enough to generate hundreds of degrees of additional heat through compression alone, circulated by super-rotating winds that carry energy around the planet 60 times faster than the planet itself turns, and capped by a permanent cloud deck of sulfuric acid that seals the system from above. Every one of these features reinforces the others. The carbon dioxide traps the heat. The heat prevents water from existing. The absence of water prevents the carbon from being removed. The density distributes the heat uniformly. The slow rotation ensures no hemisphere ever cools. The super-rotation ensures the upper atmosphere distributes energy even when the planet cannot. The sulfuric acid clouds reflect enough light to make the planet look cool from the outside, while holding a furnace beneath them that has been running without interruption for longer than complex life has existed on Earth. This is not a planet that happens to be hot. This is a planet whose atmosphere has organized itself into a thermodynamic trap of extraordinary efficiency, and understanding the atmosphere is necessary before you can understand what happens at the surface, because the surface is where the consequences of that trap become physical, where pressure becomes something you can feel crushing inward from every direction, where heat becomes something that degrades metal, dissolves electronics, and turns the carbon dioxide itself into a corrosive supercritical substance that is neither gas nor liquid, but something worse than both. The atmosphere built the prison. The surface is where the sentence is carried out. Now come down. You have entered the atmosphere from above, traveling through near vacuum at the edge of space. The first thing you notice is nothing. At 250 kilometers altitude, the gas is so thin it barely registers. But you are descending, and the atmosphere is thickening beneath you, invisibly at first, Then, unmistakably, by the time you pass 120 kilometers, drag is building. By 80 kilometers, the cloud deck appears below you. A vast, unbroken floor of pale yellowish-white haze stretching to every horizon. You enter the clouds at roughly 70 kilometers. Visibility drops. Sulfuric acid droplets surround you, fine and corrosive, eating into any exposed metal surface. The temperature at this altitude is still manageable, roughly -40 to -30 degrees Celsius, and the pressure is still low, roughly the same as the upper atmosphere on Earth. If you could somehow hover here, you would be uncomfortable but alive. But you are not alone in the sky at this altitude. The winds are ferocious. At cloud level, the atmosphere is whipping around the planet at speeds approaching 360 kilometers per hour, driven by the super-rotation that decouples the upper atmosphere from the slowly turning planet below. These winds are not turbulent gusts. They are a sustained, planet-wide river of air moving laterally at hurricane velocity, carrying the sulfuric acid clouds with it in a continuous band that circles Venus every 4 Earth days. If you were falling through this layer, you would not simply descend. You would be carried sideways at tremendous speed, dragged along with an atmospheric current that has no equivalent on Earth. The jet streams that circle our planet at altitude reach perhaps 300 kilometers per hour in their most extreme form. Venus's cloud-level winds match or exceed that, and they are not narrow bands. They span the entire planet, pole to pole, with no landmass to disrupt them, no topography to deflect them, and no seasonal variation to slow them down. You cannot hover. You are descending, and the numbers are about to change. By 60 kilometers, you have passed through the upper cloud layer and into the denser middle deck. The temperature has risen to approximately -10 degrees Celsius. Pressure has increased to roughly a quarter of an Earth atmosphere. Still survivable, still recognizable. But the sulfuric acid concentration in the clouds around you is increasing. The droplets are larger and more concentrated, typically between 75 and 98% sulfuric acid by mass, depending on altitude and layer. These are not the dilute acid solutions you might have handled in a chemistry classroom. This is nearly pure sulfuric acid suspended as an aerosol, and it coats every surface it contacts. At 50 kilometers, you are in the lower cloud deck. Temperature has crossed 50 degrees Celsius. Pressure is approaching 1 Earth atmosphere. The acid clouds are at their densest here. Below 48 kilometers, the clouds begin to thin, and something unexpected happens. The sulfuric acid rain that falls from the cloud layers above never reaches the surface. The heat below the clouds is so intense that the acid droplets evaporate before they arrive. They vaporize and are recycled back upward by convection currents, returning to the clouds to condense and fall again. Venus has rain that never lands. A chemical cycle of corrosive precipitation that exists entirely within the atmosphere, falling endlessly and arriving nowhere. Below the clouds, you enter clear air, and for a brief disorienting moment, the world almost looks navigable. Visibility improves dramatically. You can see for kilometers in every direction through a transparent atmosphere that is tinged amber but free of the acid haze that surrounded you for the previous 20 kilometers of descent. The clarity is deceptive. Nothing about this air is safe. The temperature has already crossed 100 degrees Celsius and is climbing steadily. The pressure has passed 1 Earth atmosphere and is increasing with every second of descent. But the visual openness creates a strange pause in the escalation, a window where the environment looks almost calm, while the instruments tell a story of relentless worsening. The light that reaches you has been filtered through 60 kilometers of dense haze and cloud. The sky above is a diffuse, glowing orange, like the inside of a furnace viewed through tinted glass. The sun is not visible as a distinct disk. It is a bright smear somewhere above, its light scattered and reddened until it barely resembles sunlight at all. The illumination at the surface of Venus is roughly comparable to an overcast day on Earth. Enough to see by, but dim and deeply tinted toward amber and red. And the winds, so violent at cloud level, have died almost completely. Down here, beneath the churning upper atmosphere, the air moves at a crawl. The superrotation is an upper atmospheric phenomenon. At the surface, the wind speed drops to less than 1 meter per second. A faint, hot breath moving across a landscape of rock. The contrast between the upper atmosphere and the surface is one of the most extreme in the solar system. Hurricane-force winds overhead, near total stillness below, separated by 40 kilometers of thickening, heating gas. And now, the numbers begin to punish. At 40 kilometers altitude, the temperature is approximately 170 degrees Celsius and climbing. The pressure has reached several Earth atmospheres. You are now beyond the point where any exposed biological tissue could survive. But the atmosphere does not care about biological limits. It cares only about physics. And the physics says the numbers will keep rising. At 35 kilometers, the pressure reaches roughly 6 Earth atmospheres. At 30 kilometers, the temperature exceeds 230 degrees Celsius. The gas around you is no longer thin enough to see through clearly at long distances. The density is distorting light, bending it in ways that would disorient you. At 24 kilometers, you approach 300 degrees. The steel housing of any conventional instrument would be starting to feel the thermal load. At 20 kilometers, the temperature passes 320 degrees. Pressure is past 20 Earth atmospheres. At 15 kilometers, the temperature is approaching 350 degrees. At 10 kilometers, it is nearing 400. The pressure at this point is roughly 45 Earth atmospheres. At 5 kilometers, you are approaching 440 degrees. Pressure is over 60 atmospheres. The atmosphere is so dense that you can feel it resisting your descent, not as turbulence, but as a continuous, heavy, thickening medium pressing inward from every side. The gas around you is no longer behaving like gas in any way you would recognize. It has the optical properties of a clear fluid. The refraction of light through the dense lower atmosphere bends the horizon upward, creating a visual effect in which the surface appears to curve up around you, as though you're descending into a shallow bowl that extends in every direction. You reach the surface, 465 degrees Celsius, 92 to 93 times the atmospheric pressure at sea level on Earth. You have descended through an atmosphere that, from top to bottom, subjected you to sulfuric acid corrosion, hurricane-force lateral winds, steadily increasing heat, steadily increasing pressure, and a gradual optical distortion of the world around you as the gas thickened past the point where light travels in straight lines. And now, at the bottom, the final transformation awaits. The carbon dioxide that constitutes 96.5% of the atmosphere has crossed a critical threshold at these temperatures and pressures, it is no longer a gas in the conventional sense. It has entered what physicists call a supercritical state, a phase of matter that exists beyond the critical point where the distinction between liquid and gas disappears. Supercritical carbon dioxide has the density of a liquid but fills its container like a gas. It dissolves materials that neither ordinary liquid nor ordinary gas would touch. It penetrates surfaces, infiltrates porous structures, and carries dissolved chemicals into contact with anything it surrounds. This is not a theoretical concern. NASA's Glenn Research Center operates a facility called the Glenn Extreme Environments Rig, a pressurized chamber that replicates the temperature, pressure, and chemical composition of Venus's lower atmosphere. Materials placed inside this chamber are subjected to supercritical carbon dioxide mixed with trace quantities of sulfur dioxide, hydrogen sulfide, and other corrosive species that exist in the Venusian atmosphere. The results are consistent and bleak. Most conventional metals corrode. Steels develop sulfide layers. Nickel alloys degrade. Even alloys designed for extreme environments, alloys used in jet engines and nuclear reactors, show measurable chemical attack after exposures of days to weeks. Copper, platinum, and other transition metals react aggressively with the sulfur-bearing gases. The atmosphere of Venus does not merely surround a lander, it digests it. There is, however, one recent development that offers a narrow path forward. In tests conducted at the Glenn Research Center, researchers demonstrated that integrated circuits built from silicon carbide, a compound semiconductor far more heat-resistant than the silicon used in conventional electronics, could survive and function in a simulated Venus surface environment for over 21 days. That is more than 500 hours of continuous operation at 460 degrees Celsius under 90 atmospheres of corrosive, supercritical carbon dioxide. 21 days compared to the previous record of 127 minutes. The silicon carbide circuits did not merely survive, they operated, processing signals and performing logical functions in conditions that would destroy any conventional computer chip in seconds. This result, while still limited to simple circuits rather than the complex processes needed for a full lander, represents a genuine technological breakthrough. It suggests that in future missions to Venus might eventually deploy instruments capable of surviving on the surface for weeks or months rather than minutes. The engineering is still in its early stages, but the principle has been proven. Materials exist that can resist the Venusian environment for meaningful durations, if the mission is designed around them from the ground up. The surface beneath the atmosphere is basaltic rock, confirmed by X-ray fluorescence measurements taken by Venera 13 and Venera 14. The composition is similar to oceanic basalt on Earth, which suggests a volcanic origin, and the surface is not ancient. Unlike the Moon or Mercury, which preserve impact craters billions of years old, Venus's surface is relatively young in geological terms. Crater counts from the Magellan Orbiter's radar mapping in the early 1990s indicated an average surface age of roughly 300 million to 600 million years. That is young by planetary standards. It means something erased the older surface, and the most likely mechanism is volcanism on a massive scale. For decades, the question of whether Venus is still volcanically active remained open. The planet's permanent cloud cover prevents direct visual observation of the surface from orbit. Magellan mapped the surface using radar, which penetrates the clouds, but radar images are snapshots. They show topology and texture not change over time, unless the same area is imaged more than once and the images are compared. In 2023, that comparison finally produced a breakthrough. Robert Herrick and Scott Hensley, working with archival Magellan radar data, identified a volcanic vent near Mount Mons, one of the largest volcanoes on Venus, that had changed shape significantly between two radar passes, separated by roughly 8 months. The vent had expanded and was surrounded by what appeared to be new lava flows. The finding represented the first direct evidence of active volcanic eruption on Venus observed from orbital data. In 2024, the evidence deepened. A separate team led by Davide Sulcanese at D'Annunzio University in Italy reanalyzed additional Magellan data and identified 2 more sites of apparent recent volcanism. One was at Sif Mons, another large volcanic structure. The other was at Niobe Planitia, a broad lowland region. Both sites showed radar backscatter changes, consistent with new lava flows that had appeared between Magellan mapping cycles. The findings, published in the journal Nature Astronomy, suggested that Venus's volcanic activity may be comparable in rate to Earth's, not dormant, not occasional, but ongoing and widespread. Sulcanese and his colleagues estimated that the lava flows they identified covered areas consistent with significant effusive eruptions, the kind of events that on Earth would reshape local landscapes and release substantial quantities of gas into the atmosphere. This matters because volcanism on Venus is not neutral. Every eruption releases additional carbon dioxide and sulfur dioxide into the atmosphere. On Earth, those volcanic emissions are balanced by the carbonate-silicate weathering cycle that pulls carbon back out of the air. On Venus, no such counterbalance exists. Volcanic emissions go up and stay up. Every eruption makes the atmosphere fractionally thicker, fractionally more opaque to infrared radiation, fractionally more hostile. The planet is not simply maintaining its current state. It may be incrementally and over geological time making itself worse. Now return to the Venera program and understand what the Soviet engineers were fighting against. The Venera missions represent arguably the most audacious engineering campaign in the history of planetary exploration. Between 1961 and 1984, the Soviet Union launched 18 missions to Venus. 13 successfully entered the atmosphere. 10 reached the surface. Every one of those surface missions was eventually destroyed by the environment. The engineering progression tells a story of learning through catastrophic failure. The earliest descent probes were designed for conditions that, in retrospect, were almost laughably optimistic. Venera 3, launched in 1965, was the first human-made object to reach the surface of another planet. But its communication system failed during descent and no data was returned. The engineers did not yet fully understand what the probe was falling into. As the program continued, each failed or partially successful mission returned data during its descent phase that revised the known conditions downward. The atmosphere was denser than expected. Then, it was denser still. The temperature was higher than modeled. Then it was higher again. Each successive probe was built to survive conditions more extreme than the last, and each time, Venus exceeded the new specifications. By the mid-1970s, Soviet engineers had converged on a design philosophy built around the assumption that nothing could survive the surface for long. The goal was not endurance, it was speed. Get to the surface. Collect data as fast as possible. Transmit it to the flyby bus overhead before the lander dies. Every second counted, because every second brought the interior temperature of the lander closer to the point where the electronics would fail. The landers were built like deep-sea submersibles, with reinforced titanium pressure vessels designed to withstand 90 or more Earth atmospheres of external pressure. Inside the pressure vessel, instruments were surrounded by thermal insulation and, in later missions, by chambers filled with lithium salt thermal absorption material that could soak up incoming heat and delay the rise of internal temperature. The lander would be pre-cooled before separation from its carrier spacecraft, starting its descent with an internal temperature well below ambient. From the moment of landing, the clock was running. Heat conducted through the hole, seeped through seals, radiated inward from every surface. The lithium salt absorbed it, buying minutes. The insulation slowed it, buying more minutes. But nothing stopped it. The heat always won. Venera 7, launched in August of 1970, carried humanity's first successful attempt to survive contact with another planet's surface. The descent did not go as planned. The parachute system, designed to slow the lander through the thick atmosphere, partially failed. The canopy tore or collapsed during the descent, and the lander fell faster than intended, striking the surface at roughly 60 kilometers per hour. The impact toppled the probe onto its side. Back at mission control, the telemetry signal went weak and garbled. The team initially believed the mission had failed. The data stream appeared to be nothing but noise. It was only during a painstaking review of the recorded signals, conducted after the fact by a separate team of engineers, that a faint but real temperature reading was extracted from the static. The probe had not died on impact. It had transmitted for approximately 23 minutes from the surface, sending a single measurement over and over the temperature, 475 degrees Celsius. The pressure, extrapolated from the temperature profile during descent, was approximately 90 Earth atmospheres. Venera 7 had not returned images. It had not performed surface analysis. It had done one thing. It had confirmed from the ground that the surface of Venus was exactly as hostile as the flyby data suggested. And that one thing changed everything. Venera 9, which landed in October of 1975, was the mission that first let human beings see the surface. The scientists who designed the camera system had no idea what to expect. Despite the temperature and pressure data, there remained genuine uncertainty about what the landscape would look like. Some researchers speculated about smooth, eroded plains, shaped by whatever dense atmospheric processes operated at the surface. Others suggested volcanic terrain, jagged and fresh. A few still held out hope for evidence of past water, erosion channels, or smoothed sedimentary features that might confirm the lost ocean hypothesis. What the camera returned was none of these and all of these at once. The panoramic image showed a field of angular, slab-like rocks, flat and broken, lying on fine-grained soil under a sky of uniform. Dim orange. The rocks were sharp-edged, suggesting they had not been weathered by flowing water. The soil between them was dark and granular. The horizon faded into a dense haze that swallowed detail beyond a few dozen meters. There was nothing alive. There was nothing that had ever been alive. The landscape had the stillness of a place that had been exactly this way for a very long time, and would remain exactly this way for a very long time to come. The scientists who first saw the image described a mix of awe and loss. They were looking at the surface of another world, a genuine achievement. But the world they were looking at was dead in a way that the word dead barely captures. Venera 10, landing 3 days later and roughly 2,000 kilometers from the Venera 9 site, returned a similar panorama. More rock, more barren terrain, similar lighting. The consistency was itself a finding. Venus did not appear to have regional variation in surface conditions at the resolution the landers could observe. It was uniformly bleak. The crown achievement of the program was Venera 13, which landed on the 1st of March, 1982. The lander survived for 127 minutes on the surface, far exceeding its design life of 32 minutes. It returned 14 images, including the first color panoramas of the Venusian surface. It deployed a mechanical drilling arm that extended from the lander's body and pressed against the surface rock. The drill bit into solid basalt while the lander's exterior was being baked at 457 degrees Celsius under 89 atmospheres of corrosive supercritical gas. The sample had to be collected, retracted through a port in the hull, and delivered into a hermetically sealed analysis chamber that was maintained at 30 degrees Celsius and roughly 1/20th of an Earth atmosphere of pressure. The thermal gradient across the wall of that chamber was staggering, over 400 degrees separating the interior environment from the exterior inferno, held in place by insulation and engineering that would not last much longer. Inside the sealed chamber, an X-ray fluorescence spectrometer analyzed the composition of the sample. The entire sequence, drilling, retraction, sealing and analysis, was performed autonomously, without any human operator, by a machine that had no way to ask for help and no margin for error. The composition was consistent with leucitic basalt, a type of potassium-rich volcanic rock. The color images from Venera 13 remain the most detailed photographs ever taken from the surface of Venus. They show flat, platy rocks embedded in darker soil, stretching to a murky horizon beneath a sky saturated with orange light. Parts of the lander are visible in the frame, including the drilling arm and a semicircular lens cap that had ejected onto the ground during the camera deployment sequence. The images are strangely quiet. There is no motion, no wind visible at the surface, because the surface wind speed on Venus is extremely low, typically between 0.3 and 1 meter per second, a gentle drift that belies the violence of the upper atmospheric winds circling the planet at hundreds of kilometers per hour overhead. The surface of Venus is still in the way that the bottom of a deep body of water is still, a heavy pressurized calm beneath a turbulent upper layer. Venera 14 landed roughly 950 kilometers southwest of Venera 13 3 days later. It survived for 57 minutes. Its surface sample indicated tholeiitic basalt, similar in composition to the oceanic crust on Earth. And then the Venera surface program was essentially over. 2 more landers, Vega 1 and Vega 2, reached the surface in June of 1985 as part of a combined Venus-Halley's Comet mission. But their primary scientific focus was on atmospheric measurements during descent, rather than extended surface operations. The Vega landers each transmitted surface data for roughly an hour before falling silent. Since 1985, no spacecraft has operated on the surface of Venus. That is over 4 decades of silence. In that same period, humanity has landed multiple rovers on Mars, some of which have operated for years. The Opportunity rover functioned on Mars for nearly 15 years. The Curiosity rover has been operating since 2012 and continues to function today. Mars is hostile, but its hostility is manageable. Thin atmosphere, cold temperatures, dust storms, nothing that well-designed engineering cannot handle over extended durations. Venus is a fundamentally different engineering problem. The challenge is not one hazard. It is the simultaneous combination of heat that destroys electronics, pressure that crushes structures, and chemistry that corrodes materials, all operating at once, all reinforcing each other, and all present from the moment of landing until the moment the mission ends, which, on Venus, is the same moment the engineering fails. There is no shelter. There is no shade. There is no pause. The environment attacks from every direction, through every pathway, thermal, mechanical, and chemical, simultaneously and without interruption. On Mars, if a rover encounters a dust storm, it can wait it out. If a circuit overheats, the cold Martian night will cool it. If a mechanical arm jams, engineers have days or weeks to diagnose the problem and upload a fix. The Martian environment is harsh, but patient. It allows time. Venus allows nothing. From the instant a lander touches the surface, every material in the spacecraft is being heated toward failure. Every seal is being pressured toward rupture. Every exposed metal surface is being chemically consumed by the supercritical atmosphere surrounding it. The failure is not a possibility. It is a certainty. The only variable is when. This is why the next generation of Venus missions is approaching the problem differently. NASA's Da Vinci mission, currently planned for launch in the early 2030s, will send a meter-wide spherical descent probe through the Venusian atmosphere. The probe is designed to measure atmospheric composition, temperature, pressure, and wind conditions during a roughly 60-minute descent through the clouds and lower atmosphere, capturing high-resolution images of the surface terrain below during its final kilometers. Da Vinci is not designed to survive on the surface for an extended period. It is designed to extract as much data as possible during the descent itself, treating the journey through the atmosphere as the primary science target. The probe is built to withstand the conditions it will encounter during its fall, shielded inside a pressure vessel constructed to operate under Venus surface conditions for a limited time. Even so, the engineering challenges are formidable. Every instrument, every seal, every electronic component must function while the surrounding environment rises toward 465 degrees and 92 atmospheres. NASA's Veritas mission, an orbiter designed to map Venus's surface and subsurface using synthetic aperture radar and infrared spectroscopy, would study the planet from above without descending into the atmosphere. It would produce maps of Venus's surface at far higher resolution than Magellan achieved, allowing scientists to detect ongoing geological changes, identify volcanic activity, and study the planet's tectonic and thermal evolution. The European Space Agency's Envision orbiter, planned for launch no earlier than 2031, would perform complementary observations, mapping surface composition and atmospheric structure with a different instrument suite. However, as of the current moment, the future of these missions is uncertain. NASA's proposed budget for fiscal year 2026 included significant cuts to planetary science, and both Da Vinci and Veritas have appeared on potential cancellation lists. The 2026 appropriations bill allocated funding for Da Vinci to continue, but at reduced levels. Veritas' work is described as ramping up slowly, and its launch date has already slipped from its original target to no earlier than 2031, with a risk of further delay to late 2032. ESA's Envision depends partly on NASA's Deep Space Network for communication support and on a NASA-provided radar instrument, both of which face their own budget pressures. The planned decade of Venus exploration that the scientific community envisioned when these missions were selected in 2021 is still possible, but it is no longer guaranteed. And here is what makes those budget uncertainties sting. The Magellan orbiter that mapped Venus operated from 1990 to 1994. Since then, no dedicated Venus mission from any space agency has orbited or landed on the planet. With the exception of the Japanese Akatsuki Climate Orbiter, which studied the atmosphere from orbit, but was not equipped to investigate the surface. The surface data that scientists currently work with, the images, the composition measurements, the radar maps, is between 30 and 50 years old. It was collected by Soviet landers that survived for minutes, and by an American orbiter that used early 1990s radar technology. The active volcanism discoveries of 2023 and 2024 were made not with new instruments, but by reanalyzing data that had sat in archives for 3 decades, because no new data existed. Venus, the nearest planet to Earth, the most Earth-like body in the solar system, the one world that could most directly inform our understanding of how rocky planets succeed or fail at maintaining habitable conditions, is the least explored terrestrial planet in the inner solar system. Mars has been visited by orbiters, landers, rovers, helicopters, and sample collection missions. Mercury has been mapped in detail by the Messenger orbiter. Venus has been functionally neglected for a generation. The reason is the difficulty. The same features that make Venus scientifically critical make it operationally hostile. Every mission to the surface is an exercise in controlled failure, a race to collect data before the planet destroys the instruments collecting it. Every orbiter must peer through the thickest permanent cloud deck of any rocky planet and extract surface information using radar or infrared techniques rather than simple photography. The engineering cost is high, the risk is high, the mission lifetimes are short, and in an era of limited budgets, Venus loses to Mars, where rovers can operate for a decade and return thousands of images per week. But what Venus lacks in convenience, it compensates for in urgency. Because the question it poses is not academic. It is not a question about a distant world with no connection to your life. It is a question about thresholds, about how a planet that begins with every advantage that Earth possesses can cross a line and become something unrecognizable, hostile beyond measure, and permanent in its hostility. The surface of Venus is the physical consequence of that crossing. 465 degrees, 92 atmospheres, supercritical carbon dioxide corroding every surface, sulfuric acid cycling through the clouds above, active volcanoes replenishing the atmosphere that sustains the heat, and a silence unbroken by any human instrument for over 40 years, because nothing we have built can survive there for more than an afternoon. The question that remains is not what Venus is. The science has answered that with brutal clarity. The question is what Venus means. There is a photograph that almost nobody has seen. It was taken on the 1st of March, 1982, from less than a meter above the ground by a camera bolted to the side of a Soviet lander that had minutes left to live. The image shows flat rocks, the color of dried clay, stretching in every direction under a sky that glows, a deep, suffocating orange. There are no shadows in the way you would expect from sunlight. The illumination is diffuse, directionless, coming from everywhere and nowhere at once, filtered through an atmosphere so dense that the concept of a clear sky has no meaning. In the lower corner of the frame, you can see part of the lander's base plate and, resting on the soil beside it, a small metallic disc. That disc is a lens cap. It popped off the camera housing during deployment and landed on the surface of Venus, where it has remained undisturbed for over 40 years. No wind strong enough to move it, no rain to erode it, no living thing to brush against it. Just heat and pressure and silence. That lens cap is the loneliest human artifact in the solar system. It sits on a world that is, by every structural measurement, almost identical to the one its builders lived on. And it will never be retrieved, because the surface it rests on is a place that human engineering can only visit for minutes at a time before being destroyed. Venus does not feel like a foreign world in the way that Jupiter or Saturn feels foreign. Those are gas giants, enormous and alien, with no solid surface and no pretense of similarity to Earth. Mars, though rocky and cold, is clearly a different kind of planet, smaller, thinner, drier, with a ruddy desert landscape that announces its otherness immediately. Venus offers no such distance. Venus is the same size, the same mass, the same rock, the same neighborhood. If you knew nothing about its atmosphere and were handed its physical specifications on paper, you would assume you were reading about a second Earth, orbiting slightly closer to the same star, warmed by the same light, built from the same blueprint. The shock of Venus is not that it is hostile. The shock is that it is familiar in every way except the one that matters. That one difference, the atmosphere, changed everything. And the question that remains to confront is whether Venus was always destined for this outcome, or whether it was once something gentler that fell. The scientific debate on this question is active, unresolved, and consequential. For years, the leading narrative suggested that Venus may have had liquid water on its surface for a substantial period of its early history, possibly for as long as 2 to 3 billion years. Climate models published by NASA's Goddard Institute for Space Studies showed that a slowly rotating planet like Venus could have maintained temperate conditions even at its closer distance to the Sun, provided it had enough cloud cover to reflect incoming sunlight and enough surface water to sustain a stabilizing climate cycle. In these models, early Venus was not a jungle world or a swamp planet, but something more nuanced. A warm, cloudy world with shallow seas, moderate temperatures, and an atmosphere thick enough to hold water but not yet dominated by carbon dioxide. The runaway greenhouse in this version of events was not inevitable from birth. It was triggered, possibly by a period of catastrophic volcanism that overwhelmed the planet's ability to regulate its carbon cycle, tipping the atmosphere past the point of no return. If this narrative is correct, Venus spent billions of years in a state that might generously be called habitable before a geological event drove it over the edge. The implication would be staggering. A planet that was functionally Earth-like for longer than complex life has existed on Earth, destroyed by a volcanic paroxysm that no geological process could reverse. But in 2024 and 2025, the picture shifted. Newer models incorporating updated estimates of Venus's interior water content, atmospheric evolution, and isotopic data have increasingly suggested that Venus may never have been truly habitable in the way those earlier models proposed. These studies argue that Venus's interior was likely dry from very early in its history, that any surface water was lost rapidly, and that the window of potentially moderate conditions, if it existed at all, may have lasted no more than a few 100 million years. The deuterium to hydrogen ratio in Venus's atmosphere confirms ancient water loss, but the noble gas profiles, particularly argon and neon ratios measured by Pioneer Venus and the Venera probes, suggest a primordial atmosphere that was never as strongly modified by water or biological activity as Earth's was. If Venus was hot and dry from near the beginning, the runaway greenhouse was not a catastrophe that struck a habitable world. It was the default outcome of a planet that never quite achieved habitability in the first place. The honest answer, as of today, is that we do not know which version is correct. The data is insufficient to settle the question, and the models depend on assumptions about early solar luminosity, initial atmospheric composition, and interior volatile content that remain poorly constrained. This is precisely why the planned missions of the 2030s matter so much. Da Vinci's Descent probe is designed to measure the noble gas abundances and isotopic ratios of Venus's lower atmosphere with a precision that no previous mission has achieved. Those measurements could distinguish between an atmosphere that was shaped by billions of years of interaction with liquid water and one that was always dominated by dry volcanic outgassing. Veritas and Envision from orbit would map the surface geology at resolutions high enough to identify whether features consistent with ancient water erosion, shorelines, sedimentary deposits, or aqueous mineral signatures exist. The answer to whether Venus was once habitable may be written in its rocks and its gas, waiting for instruments precise enough to read it. But here is what matters regardless of which version is true. Whether Venus lost its habitability after billions of years or never had it at all, the end state is the same. The planet crossed a threshold from which it cannot return. The atmosphere sealed, the heat locked in, the water vanished, the carbon accumulated, and no process operating on Venus today, or plausibly operable in the future without intervention from outside the planet, can reverse what has happened. This is the concept that gives Venus its deepest significance. Not the temperature, not the pressure, not the acid, the irreversibility. On Earth, we are accustomed to thinking about planetary conditions as dynamic, responsive, self-correcting. The climate warms, ice melts, sea levels rise, weathering increases, carbon is drawn down, the system adjusts. The planet has been through ice ages and hot periods, through asteroid impacts and supervolcanic eruptions, through mass extinctions that killed 90% of species, and each time the system recovered. Not instantly, not painlessly, but eventually. Earth's climate history is a story of perturbation and return, of a planet that bends but does not break. Venus breaks. Venus demonstrates that there exists a threshold beyond which the self-correcting mechanisms fail. The feedbacks reverse from stabilizing to amplifying, and the system moves not toward recovery, but toward a new equilibrium that is stable, permanent, and lethal. The runaway greenhouse is not a temporary crisis. It is a one-way door. Once the water is gone and the carbon cycle is broken, the planet does not drift back. It settles into a state that will persist for as long as the star above continues to shine and the volcanoes below continue to exhale. What separates Earth from this outcome is not size. Venus has nearly the same size. It is not composition. Venus has nearly the same composition. It is not age. Both planets formed at the same time. The separation comes from a handful of factors, none of which are guaranteed, and several of which are more fragile than most people realize. The first is distance. Earth orbits roughly 42 million kilometers farther from the Sun than Venus does. That additional distance means Earth receives approximately half the solar energy per unit area that Venus receives. Half is a significant margin, but it is not an infinite one. The Sun is slowly brightening over geological time, increasing in luminosity by roughly 1% every 100 million years. In the deep future, as the Sun continues to evolve, Earth will receive progressively more energy, and the habitable zone will shift outward. Models suggest that in roughly 1 to 2 billion years, the increase in solar luminosity may push Earth's surface temperature high enough to trigger a runaway greenhouse of its own. Not from human activity, from stellar evolution. The same fate that claimed Venus may eventually claim Earth, not because of anything we do, but because the Sun will not stay the same forever. The second is water. Earth has liquid water in abundance, covering roughly 70% of its surface. That water drives the weathering cycle that removes carbon dioxide from the atmosphere. It moderates temperature through evaporation and precipitation. It enables the chemistry that sustains life, and life itself participates in carbon regulation through photosynthesis, shell formation, and organic burial. Water is not merely pleasant, it's functional. It is the working fluid of the planetary thermostat. Venus lost its water, and with it, the ability to regulate its own temperature. The thermostat did not malfunction, it was removed. The third is plate tectonics. Earth's crust is broken into mobile plates that slide over the mantle, collide, separate, and subduct beneath each other. This process buries carbon-rich sediments, recycles volatiles, builds continents, and maintains the geological activity that keeps the carbon cycle running. Venus does not have plate tectonics in the earthly sense. Its surface shows evidence of widespread volcanism and regional deformation, but no clear equivalent of the mid-ocean ridges, subduction zones, and continental drift that define Earth's tectonic system. Without subduction, carbon that enters the atmosphere from volcanic eruptions has no efficient pathway back into the mantle. It stays in the air, it accumulates, and it traps heat. The fourth is the magnetic field. Earth generates a strong global magnetic field through the motion of liquid iron in its outer core. That field extends thousands of kilometers into space and deflects the charged particles of the solar wind, protecting the atmosphere from being gradually stripped away. Venus has no global magnetic field. Its core may still be partially liquid, but whatever dynamo process generates Earth's field does not operate on Venus. Without magnetic protection, the upper atmosphere is exposed to direct interaction with the solar wind. Over billions of years, this interaction has contributed to the loss of lighter atmospheric constituents, including hydrogen liberated from water molecules. The magnetic field did not cause Venus's atmospheric catastrophe, but its absence removed one of the barriers that might have slowed the loss of water. Remove any one of these factors from Earth, take away the water, or stop the plate tectonics, or strip the magnetic field, or move the planet 20% closer to the Sun, and the outcome tilts, not necessarily to a Venus-identical state. Earth is not on the brink of becoming Venus in any near-term scenario, and no credible scientific assessment suggests otherwise. But the tilt exists. The margin is real. And Venus is the proof that when enough of those margins erode, the result is not a slightly warmer Earth. It is a fundamentally different planet. This is what makes Venus more than a curiosity, more than a catalogue entry in a list of solar system bodies, more than a cautionary metaphor. Venus is an empirical demonstration conducted at planetary scale over billions of years that an Earth-sized world orbiting a sun-like star can end up sealed, crushed, baked, and permanently beyond recovery. It is not a theoretical possibility. It is a measured fact. Orbiting 38 million kilometers away, visible with the naked eye on any clear evening. And it forces a reckoning with a concept that human beings are not naturally equipped to absorb. The concept of planetary scale irreversibility. We understand irreversibility in small systems. A glass shatters, an egg breaks, a fire consumes a house. These events move in one direction, and no amount of effort can restore the original state. But we do not easily extend that intuition to planets. Planets feel permanent. They feel too large to break. The idea that an entire world can undergo a transformation so complete that it can never be undone, that its atmosphere can seal, its water can vanish, its surface can lock into a temperature regime that will outlast the species that named it. This is a scale of finality that sits outside normal human experience. Venus makes that finality concrete. It is not a warning in the abstract. It is a warning in basalt and carbon dioxide, baked at 465 degrees, pressed under 92 atmospheres, wrapped in sulfuric acid cloud, and confirmed by every instrument that has ever been pointed at it. The planned missions of the coming decade, if they survive budget negotiations and political uncertainty, will refine the story. Da Vinci will measure the deep atmosphere's composition with unprecedented precision, potentially answering whether Venus once had oceans or was born dry. Veritas and Envision will map the surface in detail fine enough to identify active geological processes and search for mineral signatures of ancient water. India's Shukrayan orbiter, if it proceeds as planned, will add further atmospheric and surface data. Each mission will sharpen the picture. But the broad outline is already clear, and no future measurement is likely to soften it. Venus is an Earth-sized planet that turned heat into a permanent condition. Its atmosphere does not merely make the surface hot. It creates a closed system in which heat is trapped, amplified by the mass of the atmosphere, distributed with merciless uniformity, and maintained by the same chemical and physical feedbacks that produced it. The pressure at the surface is not merely high. It is the direct consequence of an atmosphere that accumulated without limit because the processes that should have regulated it were destroyed. The chemistry is not merely harsh. It is the inevitable product of a world where carbon dioxide exists in supercritical concentrations. Sulfur compounds cycle through the clouds unchecked, and no liquid water remains to moderate any of it. Every lethal feature reinforces every other. The heat sustains the pressure sustains the density sustains the thermal inertia. The absence of water sustains the carbon dioxide accumulation. The carbon dioxide sustains the greenhouse effect. The greenhouse effect sustains the heat. The loop is closed. The system is stable. And stable in this context means eternal. The Venera 13 lens cap sits where it fell. The rocks around it have not moved. The temperature has not changed. The pressure has not fluctuated. The sky above still glows the same featureless amber it glowed when the camera captured it. Nothing on that surface will change in any meaningful way for as long as the sun continues to burn, because the system that maintains those conditions is self-sustaining on timescales that dwarf the existence of life on Earth. When you look at Venus in the evening sky, that bright, steady, beautiful point of light hanging above the horizon, you are not looking at a planet that failed. You are looking at a planet that followed its physics to a conclusion. The same physics that operates here. The same carbon dioxide. The same solar energy. The same volcanic processes. The same rocky mantle. Earth took one path. Venus took another. And the distance between those two paths, measured in the factors that separated them, is smaller than the distance between the two planets themselves. The most unsettling truth about Venus is not that it is hot. Heat is a number. Numbers can be large or small without carrying meaning. The most unsettling truth is that Venus is an Earth-sized world, built from Earth's materials, warmed by Earth's star, that became almost perfectly engineered against survival. Not by design, not by malice, by physics, by chemistry, by the slow, indifferent accumulation of carbon dioxide in an atmosphere that lost the one substance capable of removing it. The engineering is flawless. The pressure is precisely what it must be given the mass of gas above the surface. The temperature is precisely what it must be given the opacity and depth of that gas. The chemical environment is precisely what it must be given the species present and the energy available. Every measurement is consistent. Every model confirms it. Venus is not broken. Venus is working exactly as the laws of nature dictate a planet in its condition must work. And that is the horror. Not that something went wrong, but that everything is working. That the system is functioning. That the physics is correct. The chemistry is balanced. The thermodynamics is in equilibrium. And the result is a world where lead melts in the open air. Where titanium landers are consumed in hours. Where the sky glows with trapped heat. And where no living thing, no machine, no structure and no process has persisted on the surface for longer than 127 minutes in the entire history of human spaceflight. The surface temperature of Venus is 465 degrees Celsius. The atmospheric pressure is 92 times that of Earth. The atmosphere is at 96.5% carbon dioxide. The clouds are sulfuric acid. The water is gone. The carbon cycle is broken. The condition is permanent. And 38 million kilometers away, on a planet where water still falls from the sky, and carbon still cycles through rock and ocean and air. A species that has existed for less than the blink of a geological eye looks up at that bright point of light and does not yet fully understand what it is looking at. It is looking at what an Earth-sized world becomes when the margins run out.